Hello, everyone. 15 o'clock, so time to get started. Hello and welcome to another episode of Inside XRF. Today in our application seminars, we'll talk about polymers and how to analyze them with the XRF. And we'll go over a few examples and some general things to know and think about when it comes to analyzing these kind of materials. I would like to start, and it doesn't, okay, wrong window. We'll start with a little definition of what a polymer is, and we'll go over a few common examples. So in terms of polymers, or when we talk about polymers, basically what we mean is plastics. And as a definition, the polymer is basically what is repeated. When you look about the chemical composition, we are mostly talking about organics here, and they are basically put into a long chain, and a certain part repeats itself basically endlessly. And this is usually the part, the molecule that gives the name for the polymer. So as an example, you probably all have heard or read PET. I always have trouble pronouncing the full name here, so I'm not gonna give it a try, but you can see it's poly and then ethylene, and then that's terephthalate. So that's basically the component that is used to build this compound or this polymer or this plastic. Main application for this specific one is bottles, water and other drinks. We see them used in thin films, used in kitchen to wrap things, for example, and also for some clothes, like in textile fibers and sportswear come to mind and all that. Another example, very widely known, is PE, or simply polyethylene. It's used in a very large one. It's actually the ones that's used the most when you look at how much is produced and used worldwide. Packing, it's used in all kinds of packings, but also in construction when it comes to tubes for thinking about water pipes in houses maybe, and also for insulation purposes. Another one, polypropylene, is used for all kinds of containers, let's say. One thing all of them have in common is that, or all these three have in common, is that they are so-called thermoplastics. That means you can mold and form them at a certain temperature, and you can repeat that step. There is another few example in this next sheet, and you can see the names get even more complicated. So that's why people like to shorten them, just using the few letters that kind of describe the chemical component. And some of them are the opposite of our thermoplastics. They are what is in German called it's Duraplastics. It's basically a more hard and more permanent shape. So you basically form them once, and then they stay in that shape for a very long time. And we do have an example here just to sort of connect it with what we see everyday life. We have the ABS here, which is a very hard and resistant plastic or polymer. And you've probably all heard about these child toys, Lego or Playmobil. So they are used for that. Another interesting one is the polyatic acid, because they are biodegradable. So they are used in agriculture using these films, and they can actually stay on the field because they biodegrade. Polycarbonates, you've probably seen compact discs, even though they are kind of dying out and replaced by streaming services. But yeah, again, this one is a very hard, stable, transparent one. So even lenses can be created from them, or for example, the glasses you wear for your vision, they can also be made from polycarbonates. A recent addition here is the filaments that are used in all these 3D printers. You've probably come across one of those. It's a new technology that is rapidly developing. And all these filaments, they come on rolls and they're basically polymers. But the variety of their chemical composition is extremely wide. And I think what we want to keep in mind is that all of them are polymers, but the chemical composition and also the color comes from the chemicals or the chemistry basically used in their production. And that also gives them different mechanical properties apart also from just the color. Why do we need analytic for them? What is our analytical challenge here? Mostly, it's about quality control in manufacturing. And as an example, we have these children's toys here. And interesting questions in the analytic here. We'll come to another example later, but an interesting question is, especially for these toys, is how toxic they are and what kind of, for example, colors are used or what kind of additives are in the plastics that are used, because obviously you want to avoid your children to just play with them and, you know, do all kind of stuff, and you want to avoid any problems there. So you want to make sure that these ones are safe. And that's basically quality control. Another one is, the compliance with certain limitations. And I think the next example is just about that. The RoHS regulation, RoHS being a short for restriction of hazardous substances. There's the one in EU terms. This one applies to electronics in the wide sense. So your mobile phone, your watch, all the electronics we use nowadays, they have certain limitations on these elements in our table here. And we have, you can see we have lead, we have mercury, cadmium. There is also chrome 6 and some bromides. Again, funny names. The problematic stuff in both of these, again, organic components is the bromide. And there are certain maximum concentrations allowed in a lot of things that are used in these electronics. So we're talking about the electric boards, but we are talking about the soldering field that is used. So the question is always, how much of these elements are present in my product? And the next question for us, interesting, of course, or most interesting for us is, can we use the WDXRF to detect and quantify this? And as you can see in the table for lead, mercury and cadmium, it's no problem to directly detect and quantify them. For the other one, it's more different, because for chromium, while we can detect chromium, we cannot distinguish. We cannot tell the difference between a chrome 6 and a chrome 4 example. And this regulation only applies to the chrome 6. The same is for these ones. We cannot see the biphenyls or biphenyl ethers, but we can see the bromine. We can detect the bromine. So what we can say for these three elements, we can make a quantifying, and we can actually tell a concentration. While for the other ones, we can only detect them and then use other methods of analytics to quantify the amount. I think I forgot to mention, actually, if there's any questions, feel free to write them in the Q&A. We'll come back to them later if we find the time, or if we have some time at the end of this presentation. So feel free to get chatty. Back to the topic. When it comes to the recycling, sorry, I've just lost. So that is kind of one of the regulations we have. Another field we talk about is recycling of materials, and especially with plastics. this is getting more and more interesting. And we have basically, when it comes to these polymers, we have two approaches. We have a mechanical recycling. So we talk about cleaning, we're talking about sorting, and we are also melting it down again if it's a pure chemical, or even chopping it down into smaller pieces to be used in another process. This kind of recycling, which is only mechanically, doesn't change the chemistry. So the whole idea here basically is to take our plastic waste and make sure that we have a pure chemical or a pure amount of it afterwards to be used for the next production. And a second one, which is more chemical related and involves these steps. So apart from salting, we can also clean it with certain solvents to also get rid of a component, or even split one polymer into different ones using solvents or high temperature. This is more if our goal is to take a mixture of different polymers and split them and remove the ones we don't want, or basically how we put it here, the target of the goal of our chemical recycling is to get rid of additives and in the end up with a pure polymer again that we can reuse for making new stuff, basically. So why is this important for us? In the end, the success of these recycling steps, we need to check them with analytical means. We need to make sure that what we have left is basically the polymer we want and not a mixture anymore. So if for us, again, back to the question, can we use XRF for this purpose of checking it? And we'll talk about a few examples later. In terms of sample preparations, FLUXANA is very fond of sample preparation. For polymers, it's pretty simple. The most common way to analyze the polymers is just simply get your granulated form and just use it in a sample cup. So it's basically just, you treat it as a liquid, more or less. Though liquids and powders know different problems, but yeah, that's just sample cup, filling your sample and measuring. There is an alternative to avoid these particle effects that we obviously have from measuring a rather coarse granulate. There is these so-called hot presses. They basically combine an oven and a press, and you can just take your granulate and put it into a pressed pellet again, although there is a certain chemical treatment involved. But it helps you to get rid of some of the analytical problems that we have with a granulated sample. Speaking of the problems, we have some measurement data here. There's actually two examples that we took from our lab experience. So what we are looking at here is a table of titanium in plastics. That's our analyte, basically. So we're looking at the titanium concentration, and we are looking at a repeat of 3 preparations, basically. And this should be an example of the particle size influence on light elements. So titanium in our analytical situation, we can consider a light element. And from the left to the right, we have our granulated form. We then have a more fine form. I think in this case, the sample, we cooled it and ground it down. And the final one is the hot press or the pellet, so the bulk sample, basically. And we're looking at the relative standard deviation. So as a measure of our repeatability, I think we can see that for titanium here, the particle size effect is definitely there. Like when we have a coarse sample or a coarse granulate 3 millimeter in size, our standard deviation is higher than in the powder and in the pellet. This is following the usual rules of sample preparation and X-ray in order to want to have the most repeatable measurement situation possible. You want to have a homogeneous sample, and a granulate is not exactly that homogeneous because of orientations and a lot of basically air in between. There is another example here, which is cadmium in PVC, polyvinyl chloride. In this case, cadmium being a heavier element, we do not really see that effect. What we did here is we compared our certified value with measurements taken on a granulate on the sample as is, and then with different participations in finer form. And as you can see, there is a certain effect here, but it's not as drastic. We're talking about 10 ppm maybe. So in this case, cadmium being heavier than titanium, having a higher atomic number, the effect is not that profound or heavy. And in order to understand why, we have to talk a bit about our measurement situation again. And I think we'll start with a bit of theory. You might be familiar with this picture. We have used that in other presentations, and it's something that we need to think about when looking at polymers. And the first thing is that if we look at our sample, we have to think about the thickness of our samples. You see, when we have our X-ray exciting the sample, what we are actually measuring in XRF is the fluorescence coming from the sample at an angle. So the analyzed layer for different elements changes depending on the composition of the sample and the actual fluorescence line that we are measuring. So in our example here, our sample is the whole body of our square here. And for element A, we are measuring a lot more of the sample than for element B, depending on the energy. So what to keep in mind here when we're talking about analyzing X-rays, analyzing polymers with X-ray, is the thickness is important here. And also important is that actually the sample might be too thin. So we have to keep in mind that our machine is built of parts and elements that might actually be detected through the sample. So as a simple example, we had polymers measurement and we always found a lot of lead, simply because the shielding of the X-ray chamber is made out of lead. And you want to always have a look at that when measuring your samples, because the problem being your sample is so light that you might actually see parts of your machine. And you need to have a sort of thickness correction to get a good quantification, but you might also need some sort of shielding to prevent these, interfering X-rays to mess with your analytics. And a very easy way to do that is simply shield something, put something behind your sample. And what we found as a very good solution here is these aluminum plates. These are simple, what they call sample cups, I think. They are used for pressed pellets as a sort of mechanical stability. And you can simply put them behind your sample and the alumina will shatter all the X-ray from your equipment. So it's a good idea to kind of test and try out. This leads us to our main problem with the analytical situation here. When it comes to quantifying, when it comes to giving concentrations results for our polymer samples, we have to keep in mind that most of the polymer is simply carbon Wasserstoff, which is, yeah, hydrogen, I think it is, sorry, Stickstoff, so nitrogen and oxygen. And these elements are not measurable in practice. So basically, a lot of our sample is invisible to X-ray, and that is a very difficult thing to solve mathematically to give us a good results. In opposite, like a metal sample is 100% detectable. So this is not the case here. A lot of the sample we cannot detect and quantify with X-ray. So we have an unknown rest that has a big effect on our analytical situation, and especially for light elements, we also have to absorb, we have to observe the absorption of our matrix. So how do we deal with this? There is a few things. One way is to simply enter it manually if we get the information from another source. But there is also something in X-ray that can, and that, in the X-ray event basically that can help, and that's the Compton scattering. If we're looking at how X-ray works, we basically, we shoot our X-ray excitation at the sample, and we have all these fluorescence happening where the electrons goes crazy, and we have these jumps. But also what happens is that the excitation X-ray is scattered. And there's basically two effects here. I don't want to go into too much specifics. If you're interested, there is a lot of information about these available, how they work in terms of physical and mathematical. For us, it's only important we have two different effects happening. The first is the so-called Rayleigh scattering, which is a scattering of the excitation X-rays without changing in the wavelengths or energy. And then there is a second one, which is called the Compton scattering, or the Compton effect. This is a scattering of the excitation X-ray again, but this time with a change in the energy or wavelength. So one effect is it's basically just a bending, so to say, of the X-ray, while the other one actually changes the energy. And we can detect that, and we can use this information. And we have two examples here from methods that we use. The first one is from a wavelength dispersive unit here. We see the Compton peak here for two different samples. Both cases is, this is actually liquid, but for both cases we used 4 grams of liquid, and one is a pure oil, basically paraffin oil. So it's 100% CH2, and the other one is an acid, EHA, ethylene hexagon acid, I think it is. It basically is 80% TH2 or 78 plus 20%, 22% oxygen. This comes from the chemical formula of those two chemicals. And we can see that the X-ray or the Compton peak changes. And basically what happens, the oxygen absorbs signal. A different example, this time from an energy dispersive unit. We have similar effects here. Basically what we did, we had hot pressed pellets of different polymers here, and we were looking at the Compton peak after normalizing it to Rayleigh. Keep in mind, Rayleigh doesn't change, so we did the normalization here basically to compensate for thickness differences, to have it kind of normalized. And you can see that the Compton peak varies, and you can tie that directly to the chemical formula of your polymer. So what we have in the end is a way to estimate by X-ray measurement the composition of our polymer, or to tell a difference. And we can use that as a correction factor. So speaking about this, let's go into some details about applications. When it comes to measuring, there is basically these two possibilities. We have a standardless method, or fundamental parameter method. If we want to use this one in case of polymers, we have to describe our metrics. Otherwise, the results will be problematic. The second one is the classical calibration, where we use standards. The problem here is that, especially for polymers, there is not a lot of standards available on the market. So we have to find workarounds for that. Speaking about the non-standard method, just to give you an idea, we did some tests here. These are basically the same polymers that we used, or that we showed the Compton peaks of before. And what we did is we used the same software here, and we wanted to have our titanium calculated with the exact formula of the polymer. And the other calculation was done where we simply said the rest is CH2, basically oil. And our reference was the ash analysis. So we basically burned the polymer and analyzed the remains. So that is the reference we refer to. And we can see that the results where we actually input the formula, we give the information about the nitrogen and the oxygen and the ratios to carbon and hydrogen, it actually fits a lot better with the ash analysis. So actually, basically, when we want to use a fundamental parameter method, we have to kind of fine-tune it with the exact formula. An example for the other way is, this is actually from our list of services, if we want to call it like this. We have a specification for these analyses where we can analyze polyethylene and polypropylene in accordance to that norm. And well, you have the elements here, and that's what the samples look like in the end. So this is something we did, but we did a kind of trick here. Again, the amount of standards are very limited. So what did we do? We actually used oil standards, which are plentiful. You can buy them single or multi-element standards, and there is companies who will simply mix them for you. So you can buy all the standards you want. They come from like sort of say a master chemical, and they are readily available. And since it's so similar in terms of the chemical formula, polyethylene works exceptionally well here. And what we did with this application is we used oil standards to calibrate, and then for validation, we used a few CRMs that are available at the market. And for drift correction, in this case, we do a blank oil, which is the paraffin basically that we use, and the glass monitor as a stop standard. And that in combination gives us the tools to actually analyze. There is an example of a curve here. And this is zinc, and you can see the validation samples are in here. But yeah, our correlation is very good, and we can even go down to a very low concentration range. In terms of traceability, you remember maybe the little table we had before about the ash analysis. If there is no standard materials available and you cannot use the oil standards, you can also use you can also establish your traceability by analyzing the ash. And basically you burn your samples, and then, for example, you do a fusion preparation, and then you calculate back to the original material. Fusion is just one option. You could also use like wet chemistry and everything that is available to you. That's the part about the analytical possibilities we have. I wanted to take a little tour about the 3D printed filaments and standards that we hope to do from them right now. So the situation we have now is really interesting. We have these filaments, which are extremely good and reproducible polymers, which are also quite they are known, like they always come in the same quality. So the idea that is arise that a lot of places, a lot of people want to do that right now, is just use these filaments to print CRMs. And basically, we have a list here of different filaments available and, color and composition. And so the idea is we just print them into these little disks. We make a database and we use maybe a reference method to analyze the composition of this. And we can even use multiple filaments to create a mixture and a new standard. So this is definitely an interesting market for the future. And to give you an idea how it works, we wanted to share some experience that we had on them. So the first question about standards, it's always how stable are those for measurement. And in this case, the first table here is the reproducible of a measurement on an energy dispersive unit. And we can say from the repeatability and the deviation that there is no effect in the energy dispersive sector. The next one shows a similar experience with a wavelength dispersive unit where we use high power. So in this case, we have 2.5 kilowatts and we irradiate that piece of plastic a lot of times. So in this case, 10 hours roughly. So the interesting factor is here that we can actually see how it changes. The irradiation affects the standard here. We know similar effects from the thin films used in liquid analyzers, where the energy dispersive systems, due to the low power, don't affect the film, while the wavelengths dispersive things might. So something to keep in mind for future projects. But in general, we see this technique as a big opportunity just to get more CRMs, which is always good for analytics. What we do with the CRMs in the end, there is multiple uses, but it's always good to have more samples. And the 3D printing might be a new option to get more, basically. And yeah. So, actually, this should actually be a animated thing, but apparently I think I broke something with my presentation. So to summarize, in the end, just let's go over the point that we need to think about when we want to analyze our polymer. The first question is what elements we're looking for, and we should base the preparation on that. The next question is what kind of mathematics or application we want to use. Do we want to go for a standardless method? Then we need to know our sample. We need to know the metrics. And if we want to go for an empirical, more classical approach, we have to think about, are there standards available, or can I use something else as standard? And how do I validate my results in the end? There is always the option to cross-check, for example, via RESH or melting technology. And yeah, the new 3D printed standards might be feasible. This will be something that will develop over time. And that's it. I think I'm almost at time. I thank you very much for your attention. We'll check the questions that came in and give you an answer by email. And yeah, have a good day, and I'll see you next time. Thank you very much.